Hi, hello, welcome to VSTL Basics. In this video, we are going to discuss on top 5 interview questions in Verilog HTL. I am planning to take questions from ChatGPT and then we will discuss on each questions. So here I am asking top 5 interview questions in Verilog HTL. So my first question is what is the difference between blocking and non-blocking in Verilog? So Blocking statement is nothing but it will assign the right hand side value to left hand side immediately. In the case of non-blocking, it will assign next clock cycle only. So which means whenever we are going to implement combinational logic, we need to use blocking statement. Whenever we are going to use sequential circuit, we need to use non-blocking assignment. So how it will be deferred? So the assign statement, right? So in blocking, we will use only equal to symbol. In the case of non-blocking assignment, we will use less than or equal to. So example for each, I already have blocking statement in Verilog and a non-blocking statement in Verilog HTL in my videos. I will put those two examples in this video description. So now we are going to discuss on second question. How do we handle asynchronous reset in Verilog code? What are the some potential issue to be aware of when we are using asynchronous reset? Asynchronous reset is used in Verilog to reset the state of the module or group of signals independently of the clock signal. So asynchronous reset is typically an active low signal that is connected to reset input of the register or group of register. Here are some ways to handle asynchronous reset in Verilog. Use a reset state mission. So reset state missions can be used to manage the reset signal and ensure all the signals are set to the correct reset state. The state mission can be triggered by reset signal and it can sequence through the various reset state until the system is fully reset. We can use reset synchronizer as well. Asynchronous reset can cause metastability issue when they are not properly synchronized with the clock. A reset synchronizer can be used to synchronize the reset signal with the clock signal to avoid metastability issue. The synchronizer consists of two flip-flops that are clocked by the same clock signal and reset signal is fed into the input of the first flip-flop. The third, we can use reset generator. A reset generator is a dedicated module that generates the synchronous reset signal based on the asynchronous reset signal. Reset generator can be used to generate the reset signal that is synchronized with the clock signal and it can ensure that all the registers are reset at the same time. When using the asynchronous reset, it is important to be aware of potential issues such as metastability and race conditions. Metastability can occur when reset signal is not properly synchronized with the clock signal and it can result in unpredictable behavior or incorrect state transition. Race condition can occur when the reset signal is released too early and it can result in incorrect state transition or glitches in the output signal. To avoid this issue, it's important to properly synchronize the reset with the clock and ensure that all the signals are reset at the same time. Now we can move forward to the third question. So this describe the purpose of clock enable signal in Verilog and provide an example of how it might be used. In Verilog, clock enable signal is used to enable or disable the clock signal to the group of register, allowing them to be clocked only when the enable is asserted. This allows more efficient use of the resource and can reduce the power consumption in the design. By using clock enable, we can reduce the power consumption in the design by getting the clock signal when it is not needed. This can be particularly used in design that have large number of registers that are not readed all the time, such as in video and audio processing system, where certain stages may only be needed for a specific parts of the processing pipeline. It's important to note clock enable signal can introduce additional timing constraint as the register may not be clocked or on every clock cycle. Therefore, it's important to carefully consider the timing requirement of the design when using clock enables. Now we can discuss on fourth question. How would you go about designing a finite state machine in Verilog? What are some common pitfalls to avoid when designing FSM? So designing an FSM in Verilog involves several steps. Define the state diagram. This involves defining the states of the state machine FSM and transition between them. The state diagram can be represented using graph or table. Define the input and output. This involves defining the input that control the FSM and output that are generated by FSM. Write the Verilog code. This involves writing the Verilog code that implements the FSM. This can be done using an always block that is triggered by clock signal and uses the current state and input signals to determine the next state and output signals. Test the design. This involves simulating the Verilog code and verifying that FSM behaves as expected for all the possible input sequence. When designing FSM, there are several common pitfalls to avoid. Not considering all the possible states. It's important to consider all the possible states of the FSM and ensure that they are properly defined in state diagram and Verilog code. Not considering the timing constraint. It's important to consider the timing constraint of the design, such as clock frequency and setup and hold times for input and output. Not properly synchronizing the inputs. Inputs to the FSM should be properly synchronized with the clock signal to avoid the metastability issue. Not properly encoding the states. The states of FSM should be properly encoded to minimize the number of flip-flops and reduce the complexity of the designs. By carefully considering these factors, following the best practice for FSM design, such as using clear and documenting the design, we can create robust and reliable FSM in Verilog. Now I can discuss about the fifth question. How do we ensure Verilog code is synthesizable, and what are the some common synthesis issues to be aware of, and how can we avoid them? To ensure that your Verilog code is synthesizable, it's important to follow certain guidelines and best practice that are specified to synthesis. Here are some tips for writing synthesizable Verilog code. Use only synthesizable constraints. Verilog code that is intended for synthesis should use only constraints that can be mapped to hardware, which this means avoiding the constraints such as time, weight, hash delay, which are not synthesizable. Use blocking statement for combinational logic. In combinational logic, use blocking statement instead of non-blocking to ensure the logic is synthesized correctly. To avoid interfering latches. Latches should be avoided in synthesis because this can result in unpredictable behavior. To avoid interfering latches, always provide a default value for each signal and ensure that all the possible values for signals are covered in the code. Use clocked process for sequential logic. Sequential logic should be implemented using clocked processes which are triggered by positive edge of the clock edge. Use non-blocking statement to update the state of the sequential logic in a clocked process. Use parameters for constants. Parameter can should be used to define constant in Verilog as they can be easily modified and optimized by synthesis tool. Avoid large logic blocks. Synthesis tool can struggle with large blocks of logic to it's important it's important to break up the design into smaller blocks to make it more manageable. Use synthesis derivatives such as pragmas or attributes can be used to provide additional information on synthesis tool and optimize the design. Some common synthesis issue to be aware of include timing violation, synthesis mismatches, logic optimization issue. In timing violation can occur when the timing constraint of the design are not met, resulting in incorrect behavior or incorrect timing. To avoid timing violation, it's important to properly constrain the design and perform timing analysis. Second thing, synthesis mismatches can occur when the behavior of synthesis design doesn't match with the behavior of the RTL code. It can be caused by issues such as non-synthesizable construct, interfering latches, and other design issues. Third one, synthesis tool can sometimes optimize the logic in unexpected way, leading to incorrect behavior or performance issue. To avoid this issue, it's important to carefully review the synthesis netlist and perform post-synthesis verification. By following these guidelines and best practice and being aware of common synthesis issue, we can write Verilog code that is easily synthesized and produce the desired hardware behavior. Hope you enjoyed these 5 interview questions. Thanks for watching this video. Please like, share and subscribe this channel for more videos.